It's a pleasure to introduce Sara Kalisnik, who will be talking to us on tropical functions on the Barcode space. Thanks.
Hi. Thank you everyone for joining. I cannot see you, but I'm very excited to know that you're looking at your laptop right now and listening to me. The title of my talk is Tropical Functions on the Barcode Space, and so I'm just going to get going. So I know that there are a lot of applied topologists in the audience, but I figured you never know who's going to watch this video in the future, so I'm going to try to start in the beginning and say a couple of words of motivation for TDA in general, and then talk about persistent homology, because this is basically what I'm dealing with. We live in the 21st century, and big data sets are everywhere. And for example, if you look at gene expression data, Twitter, Facebook are both collecting data, trying to figure out what to suggest you to buy, etc. And so this data often comes in the form of point clouds in Rn. So for a point cloud means a finite metric space to a mathematician. And we face problems analyzing these data sets because they come in form of very long vectors where not all coordinates are relevant. They're very high-dimensional, noisy, and the goal of topological data analysis is to take tools from the field of topology and try to adapt them so that they would be suitable for analyzing point clouds. So what is homology? So you can think of homology as a method of that do a measurement of the space. So for example, if you look at the circle, you would say a circle is made of one piece. It has one loop. If you look at the sphere, it's made of one piece, but so it has it encloses a different kind of void, which would like a two-dimensional void, etc. And so basically, you can encode this information in terms of Petty numbers, which roughly tell you how many pieces of space is made of, how many loops it has, how many higher dimensional voids it has, etc. One of the most popular methods in applied topology is called persistent homology, and it's basically an extension of homology to the setting of point clouds. And this concept emerged independently in the work of Rossini Ferri and collaborators in Italy, Robbins with her PhD thesis at Boulder, Colorado, and Adels, Brunner, Letcher, and Zamorodian at Duke, North Carolina. So what's the idea behind persistent homology? So we start with a point cloud, and the point cloud, it doesn't have very interesting structure, because if you think of it, it's like how many pieces is it made of? Well, it's like just a number of points in that space. Are any loops? Well, not really. So the idea is to, instead of look at this finite collection of points, to thicken them slightly, to basically observe balls centered at these points, and then see what happens, and then observe the union, and that hopefully is going to give you information about the underlying space you're sampling from. So, but then of course the problem is how, if you say that you thicken your points, it's by what radius do you thicken them? And so, for example, if we look at this picture over here, what I'm tempted to say is, well, I'm sampling from a circle, but then I have some noise, which would be the tiny circle you see on the side. But I would really want to say, well, so this is a circle with some noise. But then the question is, so as I said earlier, how do we pick how to thicken the points, right? And depending on how we thicken them, we might get different answers. For example, on the left-hand side, we can see two loops. On the right-hand side, we just see one loop. So how I want to have a method that would say, oh, here I have one essential loop, and the rest I can just say is noise. And that's the purpose of persistent homology. So what's the idea? So this is not that surprising because statisticians have been observing dendrograms for quite a while. But the idea is instead of looking sort of at these secant points for a single value of R, we observe sort of how the union of these balls changes as we vary the parameters. So the information is going to be not just a single union of these balls, but sort of the union at parameters, and then of course we have natural inclusion maps between them. So basically, the object that we end up with is a collection of vector spaces with linear maps between them. So vector spaces, because when I talk about homology, I always have field coefficients in mind. So and then I'm working with vector spaces. So these structures we call persistent vector spaces, and the question is, so can we classify them? And we can by barcodes. And this is work that appeared in Computing Persistent Homology by Gunnar Carlson and Afam Zamorodian. So just to go back to an example to demonstrate how this works. So we start with the point cloud, and now we start thickening the points, and we see the first loop appearing, and then the first loop disappears. We have the second loop, which is present, and as we sort of grow the radii, it's still present, and then this one is filled in as well. So what does this barcode tell us? Well, here we can see the output are two intervals, and basically what it's telling us. So there is one shorter interval and one longer interval, and so each interval corresponds to a topological feature. So here we have two features, one I guess sort of like the circle and the tiny one over here, and so if we look at the first interval, it shows us when the tiny loop appears and then how long it persists, and the same for the second one. And sort of the idea of persistent homology is to look at this collection of intervals and then to say, well, if I have very long intervals, they should correspond to features that really do come from the data. And so just to, I guess by now there have been many successful applications of persistent homology. I'm just going to quickly mention two. So one is to the space of image patches, where sort of they realized, they found out using persistent homology that locally this space looks like a Klein bottle. And then the other one is viral evolution. So evolution, I guess, sort of in the past, everybody was talking about evolutionary trees, but if you look at viruses, bacteria, there's, and especially now, sort of when we have the ability to collect genes, you can see that there was a lot of exchange between different between bacteria, viruses, and we can use persistent homology to sort of track these non-tree-like evolutions. And this is work by the group at Columbia University. So we have a method called persistent homology, and the output of persistent homology is a collection of intervals. And so one of the problems, that we had, I guess, was how to make this method popular with people who are not applied mathematicians. And sort of, if we look at the communities, right, computer scientists, so they have a lot of tools for analyzing data sets, but most of those tools accept vectors as an input. So we have, but we, on the other hand, have an invariant that is very hard to combine with these existing methods. So the idea is we want to make a bridge sort of between persistent homology and these other methods, and one way of doing this is sort of instead of looking just at the barcodes, we attach numerical values to these barcodes, so that at the end we produce vectors, and once we have vectors, we can use those vectors as an input to their methods, for example, support vector machine if we want to classify something. And like another reason why this is a good idea, because so sometimes we're dealing with data sets where the data points themselves very interesting geometric structure. For example, if we have images or if we have chemical compounds. So sort of this allows to represent each data point as a vector, right? And then again, for example, if you want to classify them, you can use existing methods. But this, so here, we can also, like, it just helps with representing these data sets. And I mean, it's not surprising that much work has been done already. So, for example, with persistent landscapes by Peter Bubenik and Paul, and then sort of it was like written down in code with Bubenik and Diotko, and then sort of complex polynomials in like among the aliens. And just at a conference in Arkansas this weekend, I learned about a new paper by Henry Adams, Lori Ziegelmeyer, and Patrick about, well, and there are 10 authors in total, and also give a method of representing persistent homology with vectors. So my work is most similar to work done at Stanford. So the first paper came out in 2013, and basically the idea was to observe sort of the space of all barcodes, sort of varieties, and then look at like try to identify polynomials on this space. So this was work by Aaron Adcock, Eric Carlson, and Gunnar Carlson. So I'm gonna quickly describe their work, but before I do that, I use the word barcode space, and I haven't defined yet what I mean by a barcode space. So first move on and discuss, like, and say precisely what I mean with this. So I mentioned just briefly that the idea was to sort of, these spaces as varieties. And then the first thing was, well, how do we, if we have a barcode, like, so we have n intervals, how can we represent these n intervals? And like one very natural answer is, well, we can just put sort of the left endpoints of intervals and right endpoints of intervals together and form a vector. Now, this might seem tempting, but it's not exactly what we want, because so basically if we so in this way we would kind of order all of these intervals, and that's not something we want to do, because sort of basically I mean, if you have like a list of features, you don't really care what order they come in. So we still do this step sort of with with sort of put the information about a barcode within intervals into a vector, but we also take the action of the symmetric group into account, and these. So this we now denote by Bn. So this is going to be the so this is the set of orbits that we get like with the action of the symmetric group, and this is and these are all. This is the collection of barcodes of cardinality n. But we don't want to sort of, say in advance, well, I'm gonna get a bar, the output is going to be a barcode with n bars. So what we want to do next, well, we want to put all of these together. So we form a disjoint union of these barcodes of n bars each. And but we also don't want to stop there quite yet, because the point of persistent homology was, I mean, sort of just in the name, is like we are looking at how long some features are present in our filtration, and sort of if not, sort of if the corresponding vector is 0, then we would say that those objects have no persistence. So basically, we want to take that into account, so we define a relation on this disjoint union, which turns out to be an equivalence relation, by saying that, well, if I take a barcode with n intervals, so this is going to be equivalent to a barcode with n+1 intervals, in which the original n are the same, but then we add a 0 length interval. So if you have a bunch of zero-length intervals, that's not going to change your barcode, because what would correspond to those intervals has no, those features have no persistence. So if we then take the quotient of this equivalence relation, what we end up is the barcode space. But then, there is a notion of similarity on the space of all barcodes. I'm gonna review what Wasserstein distance is and what the Bottleneck distance is, and if we think about it, so we start with barcodes that have where each barcode has one interval each. So if in this situation we're going to take the distance between those two to the maxima of the differences of the x coordinates and the y, the maximum and the absolute of the difference of the y coordinates. But then sometimes because of this relation that I have, I also observe that the distance from a point diagonal, and that's just going to be the ordinary y minus x over 2. So now let's define distances between barcodes if we have more than barcodes, more than just one barcode in each. So suppose we have two barcodes, B1 and B2, and so they're both indexed by some sets. Let's say the first one is indexed by set A and the other one by a set B. And so what we now do first is we match some bars in A to some in B1 to some bars in B2. And then what we're going to do is the rest of the bars in A are going to be matched to the diagonal, and the rest of the bars in so the rest of the bars in B1 are going to be matched to the diagonal, and the rest of the bars in B2 are going to be matched to the diagonal. And for this particular matching, we're going to define a penalty of theta. And what we're going to do is, point B, each interval in B1 is matched to an interval in B2. So for this, we just take the distance between two intervals that we defined earlier. But now we want to take the minima of these distances that we get for all the matched points. So that's the first expression. So the rest of the intervals in B1 we match to the diagonal. That's the second expression. And we take the maximum of these distances. And then the third one are the intervals in B2 that are matched to the diagonal. So this is the penalty of this particular partial bijection from a subset of A to a subset of B. And now to get the distance, we take the minimum over all these bijections from some subsets of the first index set to subsets of the other. If we look at this picture over here, there's the first person's diagram has these circles, discs really, and the second one has squares. So how do we match them? Well, it's for the two, so these two and these two is kind of clear, but I mean, if you think about it, if we try to match this to this, for example, the distance would be big. So it makes more sense to to match this one with the diagonal, this one to the diagonal, and this one to the diagonal. That's what and this is how the minimum is achieved in this particular case. But this is not the only distance used on the barcode space. So also popular is the family of Wasserstein distances. So proceed in the same way with this projection of subsets of the first index set to the other, but don't take the maxima over distances between matched intervals, but we raise them to P and add everything together. So LP versus L infinity. And so this is how we get, for a particular P, this is how we get the penalty of that particular bijection from a subset of A to subset of B. And now to get the Wasserstein distance, we can take the minima over all of these bijections and then the piece root. So one of the things that are important is, for example, if we have codes and they're close, if sort of what method we have for producing vectors of our barcodes, it should sort of make sure that if two bars are close to begin with, that the vectors that we get are also close. So I'm going to go back to the work by Gunnar and Eric and Aaron that I described. So their idea was to try to identify like polynomials on the space of barcodes. And so think about it, what are the properties that need to be satisfied? So for one, these functions should be symmetric, because if we sort of give a barcode with n bars as a 2n tuple, so we don't care in what order the bars come in. And then the second condition is, if we add zero length intervals, we want this function to be the same in the barcode and in barcode with the zero length interval added. So the polynomials they identified are generated by these over here. So PAB, and what you do, you take the sums of xi1. So this is for the ith interval, like depending how it's given. The coordinates, so the left endpoint of the interval and the right endpoint. So here we have left and right endpoints, and here are the lengths of intervals. And so if you think of it, like the second condition is, if we have the length, so if we have an interval of zero length, this function shouldn't be dependent on left endpoint along that interval. So this is why there is a B over here, because sort of as soon as we have something that has like an interval with zero length, it's just gonna sort of make the the left endpoint part to go away as well. So these functions they're fairly easy to describe, but like one drawback to actually to use them is that they're not stable with respect to both the distances I just mentioned. So when I say stable, I mean basically sort of Lipschitz, but sort of here is the condition. So how do we proceed? I mean, clearly, this is not a desirable property. So basically, the thinking was, what kind of functions should we try to find so that they're going to be stable with respect to these two distances that we have on the barcode space? And so if you think about how I defined the barcode space, you can see sort of that the maxima were pretty prominent, sort of, and that made us think. So instead of looking at like the ordinary rules with addition and multiplication, which is basically how you get ordinary polynomials, maybe you should work in a different kind of, like with a different kind of arithmetic. In particular, we thought of tropical semirings, because in tropical semirings, the addition is replaced with a minimum, and multiplication is the ordinary addition. To know, tropical algebra is a fast developing field in its own right, but the name actually was coined by French mathematicians. So basically, one of the first people to wrote about these semirings is Imre Simon, who is a Brazilian mathematician. And the French mathematicians basically wanted to name this whole field in his honor, and because they perceived Brazil as a tropical country, they named the field tropical algebra, tropical geometry, and the semiring, the tropical semiring. earlier that so the addition in the tropical semi-ring, if we take two elements, we really take means taking their minimum, and multiplying two elements together is just adding them in the ordinary arithmetic. So if we look, for example, so we have 4 plus 5 in the tropical arithmetic. That's going to be the minimum of 4 and 5, which is 4. If we multiply this by 3, it means we add 3, so we get 7. Sort of just we define ordinary polynomials, right? It's like we have variables, and then we multiply the variables together, and then add sort of these multiplied variables together to get polynomials. We do the same thing in this setting. So a min plus polynomial expression is gonna, so we obtain these expressions by taking variables, but now we tropically multiply them, and then we tropically add them together. And for each expression, we can define a total degree by just taking the maxima of sums. So you might be wondering why I didn't say tropical polynomial expression, because these are tropical semi-rings after all. But in fact, this expression is already reserved for something else, namely, so in algebra. So when we talk about min plus expressions, it means that the exponents are always going to be non-negative. But in tropical algebra, you can, so it's like you basically don't have polynomials, but you have Laurent polynomials. So these A's can be negative as well. An example of an expression. So if we have x squared plus 1x plus 4 in the tropical arithmetic, so 1 times x is going to be 1 plus x, 4 is 4. X squared is going to be 2 times x, and then add everything, we take the minimum. So the side of the spectrum is the Arctic semi-ring. So it's so in the community, most people call it the max plus semi, but I kind of like the sort of duality between the tropical and Arctic, so I insist on calling it the Arctic semi-ring. And so basically, so it has very similar structure to the tropical semi-ring, but here when we add two elements, we take their maximum. So for example, here we have 4 plus 5, so that's the maximum of 4 and 5, which is just 5. We multiply by 3, we get 8. And 4, we can now form max plus polynomial expressions. Sort of for these expressions, I assume that the A's are all non-negative. And we define degrees of these expressions in the same way. So the first problem, I guess, that we face is, sort of like when you think about these expressions, you can represent, so we are interested in functions, but every function obtained this way can be represented by expressions in many different ways. For example, if we go over here, x1 squared plus x2 squared in the tropical arithmetic is the same as x1 squared plus x2 squared plus x1 times x2, because, so basically this is an average of these two. So like but the minimum is never attained in this expression, so it's really redundant. Because we are only interested in functions, but not sort of, we don't want to treat all of these expressions that represent the same functions differently. So I find an equivalent relation on these rings of expressions. Namely, two expressions are equivalent if they define the same function. So now, if I take the semi-ring of tropical expressions and sort of and then the equivalence classes with respect to the relation, I get what I call tropical polynomials. So that's why I differentiate between expressions and polynomials. When I talk about tropical polynomials and min plus polynomial, max plus polynomials, I really have functions in mind, not and each function can be represented by more than just one expression. And so similarly, min plus polynomials, max plus polynomials. But then it's like we don't have to stop there. I mean, sort of with like so in the real world, right? It's like we look at rational functions. There's nothing preventing us to define tropical rational expressions in this case either. So basically we're here that we have -1, so this would just mean p of x minus q in the ordinary arithmetic. We are interested in functions that they define and not different expressions. So we also look at an equivalence relation on the tropical rational expressions, and this way we get tropical rational functions.
Sarah?
Yes?
If you can go back, so for the rational expression, q inverse, that is just minus q, is that right?
That's correct.
So this is the minimum of p and minus q. This is what tropical rational expression is. Yeah.
It's going to be so it's going to be minima of some things minus minima of other things.
Yeah. So we see a -1, we should think negative, right?
Exactly. Yeah.
Okay.
That's correct.
Thank you.
Okay. So, and I said earlier, so what are the kind of functions we're looking for? And the first condition is that they are symmetric. And so I really, so when I was when I started working on this problem, of course, the first thing you do is you look at the sources. And sort of the fundamental theorem of symmetric polynomials is like it's a very basic thing. And sort of given that sort of tropical algebra field is developing like really fast, I was really surprised to learn that nobody has done any invariant theory in the tropical setting. Which, I guess it's not bad, but it's like I had to go into that. And I'm going to mention a couple of results I got with these, with respect to this. And so, I mean, if you think about it, for barcodes, we have pairs that we permute. And a simpler question is to just look what happens if you have n entries and you permute them. So that was sort of a starting point. And so a max plus polynomial is symmetric if p is preserved. So if we have points and then we permute the entries if it's preserved under that. And sort of an analogy with ordinary symmetric polynomials, we can define elementary symmetric max plus polynomials, where we basically replace the operations with these like either tropical or Arctic operations. So, and it turns out that if we look at all the max plus polynomials, so that every expression can be, so that every max plus polynomial can be written in terms of these elementary symmetric max plus polynomials. Although sort of you might see that the uniqueness statement is lacking, but that's sort of for the reasons I mentioned earlier. There's a lot of redundancy in these semi-rings. On to the two symmetric case. So what we have with barcodes is so we have intervals which is encoded by each interval is encoded by 2 points, and the operation allowed is, well, we can permute these pairs. We call the max plus polynomials that are invariant under this kind of action two symmetric max plus polynomials. And so the idea with the ordinary polynomials barcode space was to give like specific functions that people then use as coordinates. And sort of I intend, so like my goal was to do the same thing in this tropical setting. So now like how will we encode these? So first let's sort of notice that if we're given a matrix, that any matrix is going to determine a max plus polynomial. So for example, over here we have n equals 3, so that means we take like we have 3 barcodes. And we take E. So matrix over here, and and what we can think is, well, so this is entry 1, 1 of the matrix. So I take x1, 1, and root to 1. And now all operations are in the arctic semi-ring. And then, so here it's 0, so I don't have x1, 2. And then, so, but then, like for position 10, I have 1. So this is going to be x2, 1, and so here's 0, here's 0, and the next expression is going to be x3, 2. So from a matrix, I can get a monomial. And so for the ordinary symmetric cases, like we have some we have those basic polynomials that we basically get by multiplying them together and adding them. And so we're going to do the same thing here. So, and sort of try to make them as simple as possible, which is the reason why here I'm just using the entries from the set with just with 2 elements, 0 and 1. So for every such matrix, I can get a monomial, but that monomial, I mean, as you saw earlier, is not necessarily going to be too symmetric. So what I do is I look if I permute the rows, because this is the option that I have, and sort of and get all possible matrices that I can obtain. So the orbit of this, like for the orbit of action, if I then add all of those monomials obtained in that way together, I'm going to get 2 symmetric max plus polynomials. So, for example, so this is the matrix from earlier. So this was the first expression, but this expression is not this is not too symmetric max plus polynomial yet. So then I just add over like the whole orbit. So what can I do? Well, I can change rows. So it's like, so I have 3 probabilities: 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, and 0, 1, 1, 0, 1, 0. So just to make it easier, these are the kinds of expressions that we get. So these are maxima of linear combinations of these of the x's. As opposed to the ordinary polynomial case, so this was something that was researched extensively by Dalbeck. The polynomials are finitely generated, but this is not the case in the max plus in the Arctic semi-ring. So basically, this just demonstrates that the situation is a lot more difficult in these semi-rings than it is in the ordinary symmetric case. Yeah, so let's see what we can still salvage from this. So I'm just for the sake of operation. So it's like you saw that. So we have maxima and I add things together. So I'm going to slightly modify my definition of the barcode space in the sense that I'm going to specify each vector not by left and right endpoint, but by left endpoint and by the of that vector. So that's going to be in position of that interval. That's going to be in position 2. And I'm going to additionally assume that they're all positive. So that's so the reason for this is comes from the Arctic semi-ring. I can explain during the question session or later. And so then the next step is, so what I first just look among the 2 symmetric max plus polynomials. So this would be like a result equivalent to the one by Eric, Gunnar, and Aaron in their paper. So this is the list of generators that I get. So dn is for barcodes with n intervals, and then I sort of put everything together to get expressions on the whole barcode space. But you can see, so again, just for translation into the ordinary arithmetic, what you can see is I get maxima, and then I'm building expression by taking, so first maxima of all the lengths of intervals, then maxima, and I add lengths like of 2 together, and then sort of go over all combinations, and then finally add all the intervals together. And I mean, and then set the like max plus 2 symmetric polynomials on the entire space D. We get so we just put together, as I said earlier. So now, the good thing is that these functions are stable with respect to the distances we normally use, but the problem is, and which I guess you can see because you're looking at the functions in front of you, is that there are no x's involved. And so it's like basically we don't have enough functions to actually separate the barcodes, which is not desirable, to put it mildly. Okay. So,
quick question. I go back to that. I was hoping you could just remind me notation. So these E and then their subscripts are these matrices.
yeah.
You know,
So,
the
yeah.
angle 0, 1 or the row 0, 1. The power is the power just telling you the what's the power you?
So they're telling me how many rows have 0, 1 in them.
Okay.
Yeah.
Right,
basically, so then would be 0, 1, 0, 1, and the rest of the rows are 0.
And then which rows have 0, 1s because you're doing this?
We're permuting them.
Yeah.
Yeah. So basically then, so we don't have enough functions, so we have to include more. So unfortunately, like you don't you can find a file. If you look at the whole barcode space, you cannot find like a finite subset of these things to separate the barcodes. You do if you sort of limit yourselves to a particular dimension, you can do it. And also, so max plus 2 symmetric polynomials, I was actually able to say, so these are all the functions that you get, right? Sort of that satisfy these properties. But like because these are not enough, I had to go one step further and look at these tropical rational functions. And over here, I mean, if you look at those conditions, it becomes possible to say, oh, like these are all the functions that you get. So at this point, I give up on trying to describe like in all detail this space. But I guess the goal was to find enough functions and not to necessarily find all of them. So I'm going to start sort of with the elementary two-symmetric max plus polynomial that I defined earlier, and I'm going to define like a whole like new family of modified polynomials as follows. So basically, instead of taking like x1 d1 as an entry, I changed the x coordinate slightly. So this is going to be the x1 and m times d1, and the reason for this is for like that condition to be satisfied. So it's like if I add 0 length intervals, then my functions have to be independent of x. So that belongs to the left endpoint of that particular interval. And basically, sort of taking this over here ensures me that, well, if the interval has 0 length, this is just going to be 0, and I'm not going to have to deal with that x anymore. So these are sort of the functions that I now observe obtained this way, and it turns out that they are stable with respect to the bottleneck and Wasserstein distances, and you know, it's like they are like relatively easy to describe, and like if you so it's sort of in practice, basically, it's like what the parameter values are. I mean, they're usually like bounded by some number, right? So you can, so basically what these functions do is, for example, like later I'm going to look at pictures with 28 times 28 pixels. So this D1 is going to be bounded by 28 if we take like 1 pixel as a measure. And if I take M to be 28, so then basically this expression is going to equal x1 as long as D1 is not 0. Sort of it's going to be the same functions you saw earlier, but just sort of this little modification is needed so that they're actually going to satisfy this condition of adding zero length bars. So the functions, they're stable, and now we actually do have enough of them to separate between barcodes. And sort of, if you give me 2 bars of I know what dimensions there are, I can give finitely many of these to distinguish between them. And just to show, sort of, I have minutes left, see how this works in practice. So when Aaron and Eric and Gunnar were sort of wrote a paper about their polynomials, they tested it on the MINST data set, which was collected. I think like for this particular period, they asked U.S. employees to write digits, and then then the goal is to sort of figure out, like to figure out which is 1, 2, 3, etc. So they did that using persistent homology, and so the idea is, like, I mean, if you do just one filtration, it's not going to work, right? So we do filtrations from up to bottom, bottom down, left to right, right to left, and then, for example, if you look at 6 and 9, if you do from bottom to top, in both cases, it's going to detect that loop in different places. So this is sort of how you're able to distinguish between the different digits. So they used these functions over here, and these are the results that they got. So I used my functions. I mean, I think it's really hard to compare these methods. I mean, I got better results, but it's like these functions are different. Sort of, I guess, as I said, these we actually have guarantees that they're stable. And I guess sort of one of the interesting things is, so I said earlier, well, you know, for the two symmetric max plus polynomials, I can actually tell you like how to get all of them, right? I can give you the generators. And so it's sort of, I got best, like when I was trying out these different functions, I got the best results when I was just using these combinations of lengths of intervals. And I feel that sort of in a way, and that's kind of in line with the whole theory of persistent homology, like where you look at the intervals and length, you know, sort of the idea is, well, we look at like the lengths of intervals because that's going to tell us sort of what features are important, right? So here, these things still capture like much of the information needed. Although, I mean, I did use one of these functions as well. And so it's like, so finally, where did, why are only, I don't know, 90 points times something of these images recognized? Well, because it's like there were some digits like this one over here, right, where like you have a 9, but it doesn't really have a loop, and then like 8, but like 8 has no loops, right? And then what's this? It's a 3, I'm not even sure what it is, has a loop when it shouldn't. So I'd like to finish with this, and thank you for listening to me. And I'm going to be happy to take questions now.
Thank you, Sara. We start with who has questions.
So out now. So did I actually see you on the camera? Is that it? Okay, well, good.
You can, yeah.
Mhm.
I'll start. So on the application you gave, so you chose some subset of your trouble expressions that you know distinguish between barcodes, and you come up with, so you wanted a finite list, I guess, and so you have here.
So classification results, sort of.
Is that right? You've got this list of, I guess, 6?
Yes. So how did I choose these 6?
How did you end up with that choice of 6?
Okay. So basically, you know, like when Aaron, so I was talking to Aaron, like one of the authors of the first paper, and said, well, how did you choose the first 4 functions? And he basically said, well, I tried like different types, and these gave the best results. So basically, so I did the same way. I mean, sort of, you know, like just theoretically, it would seem the more functions that you use, the better like classification you should get. Somehow, if I use too many functions, I started getting worse results. And I mean, I think that probably has to do something with like the dimension going up. But I basically tried different things, and sort of for these particular functions, I got the best results. And it did help adding more functions. It's like at point adding, I mean, sort of, it started being really slow, but also it started recognizing like fewer of the digits.
Okay, thanks.
This max plus ring think, of two symmetric polynomials is not finally generated. Is that hard to show or easy to see? I mean, maybe it's not easy enough to explain verbally, but.
I mean, so this paper, like, that deals with the whole tropical stuff, is already published, and it's online, and the proof of this is online. Basically, I mean, it's by contradiction, right? It's like you try, I mean, like you say, well, let's suppose there are finitely many of them, and then just produce something that cannot be generated by it.
Okay.
I mean, it's sort of, if you look at the the 2x2 examples, I think it was I forget. I think it was sort of, like belong to matrices of the type 1D D1. Sort of, for those, like, you couldn't write in terms of these elementary symmetric, like, two symmetric ones. But basically, like, proof is by contradiction.
Thank you.
Can you also tell us about the assumption that X is positive?
Yeah. So I think, I mean, I don't think that's like a really rough assumption in a sense, because sort of, if you thought it, like, what are the illustrations that we usually use, right? I mean, it's like we usually start with data, like with a point cloud, and then we build either RIPS complexes or check complexes, and it's like, so these parameters are then always, like, positive, right? It's like these are always positive. So, I mean, this is what X would be, right? Because when, like, for which R does it appear? But sort of the reason why I assume this is, so basically, like, if I assume that I have a space with just, like, with n bars, I'll tell you, what the functions are. But, then it's like we have to, like, because we have now this disjoint union, like, for the barcode space, we somehow have to be able to get from one to the other with maps in between, right? And sort of the natural inclusions are sort of, if you are in say R2 into R4, is to just add 0, 0. But but basically the thing is that so it's like, this is the reason why it didn't work with min plus expressions, because sort of basically the problem is that 0 is not like the neutral element in these rings, right? Like, unlike the case with ordinary polynomials, by ensuring that X and D are both greater or equal to 0, I kind of forced it to be, and that's why the algebra of putting these polynomials together worked in a good way. If that makes sense. I do.
So for extending a barcode with 4 bars into one with 5 bars, what do you?
Just add 0, 0.
Okay, but I thought it wasn't in the. Is 0?
Yeah, that's a lot. And X, D are greater than or equal to 0.
Greater than or equal to, okay.
Yeah.
Okay.
Like, the most natural thing to do, right? But somehow, I mean, if you, like, you can have trouble. I mean, it's basically because like, 0 is not a neutral element in these rings. I need it to be.
Okay.
Yeah.
Other questions? Thanks, Sarah. So thank you very much.
Yeah, look, so much. Yeah, I've never given a webinar talk before.